Okay, and base current. Okay, so he in the same diagram, one if you apply KVL at the input side, at the output side we have written the equation. If you apply KVL at the input side, you have to use this path. So one voltage is VCC, one voltage is VBE, the resistance is RB, the current is IB. So I can write VCC minus VBE equal to IB into RB. VCC minus VBE equal to IB into RB. So from this I can find what is IB. So IB equal to VCC minus VBE by RB. See, most of the case VBE value, what is the VBE value? Yesterday you told the VBE value for silicon and germanium. What is the VBE value? What is the VBE value for silicon and germanium?
0.7 and
Yes.
0.2.
Yes, since it is VCC is 12 volt, when you compare the 12 volt, this VB is very, very small, right? So mostly what they will do, they will ignore this VB. But if you want to get actual resistance, you have to include. But since the range of VCC and VB are quite far apart, they will ignore this VB. So I can write IB equal to VCC by RB. It is approximate expression. But actual expression is IB equal to VCC minus VBE by RB. That is what is given here. You can see here. So the approximate current is IB equal to VCC by RB. But actual current is IB equal to VCC minus VBE by RB. And in market, no two transistors can be exactly same. If you have two transistors in your hand, they're exactly same in dimension, parameters, everything, but they will not behave in the same way. Okay, so when you just replace a transistor with another transistor, you cannot expect the same behavior from the circuit, even though both the transistors are going to be identical. எல்லாமே perfect பண்ணா கூட when you put the transistor in an external circuit, it will not, both the transistors, there will be slight variation in behavior of both transistors. I think I usually say this, there is nothing like an ideal case, right? So things which are very ideal will not work out in practice. So same way, so even though you have two identical transistors, what you claim, but the two identical transistors will not give the same behavior when they are put in different electrical circuits, because there will be some variation in IC, some variation in IB. Because of that, the beta is also going to change. So if one transistor, if I use point exactly in the middle of my DC load line, if I change the transistor, the Q point might be slightly shifting upwards or downwards. So that's what we say, for every transistor you are going to use in your circuit, you have to completely redo the design again. You cannot use the same design values, you have to redo the design again. Okay, so that's what they have say. So in the output characteristics, you might expect some change when you are going to replace the transistors, because it may lead to shifting in Q point, which will become unnecessary, and the amplification behavior of the BJT will not be expected. Okay, so don't think all transistors will have same parameters. Ideally, yes. Practically, two transistors, even though they're having all parameters, VB is 0.7, beta 100, everything is same. When you connect them in external circuits, you cannot expect them to work as same behavior. You cannot expect them to provide the same behavior. Okay, so any doubts you have in DC load line? So I have explained you about how to draw DC load line. DC load line, this equation, if you remember, this equation is used for finding your DC load line. VCC equal to IC into RC plus VCE. So one condition is you have to put VCE equal to 0, you get one end of load. Another condition is you have to put IC equal to 0 to get another end of load line and join them. You get your DC load line, and the Q point will be exactly in the middle of your DC load line. Simple. Any queries you have so far, you can ask now. Once you are thorough with DC load line, we can go for AC load line. Please feel free to ask any doubts you have so far in the class. And to understand these circuits better, what I will do, we have a software called Multisim. So Multisim is an online simulator software which we have. So there we can simulate all these circuits and see what values we get. Okay. So I will be showing you the live simulation of all these circuits once we start analyzing the biasing circuits one by one. Okay, so it is clear. The multi-sim software is very simple. It is drag and drop. Even you can create your own online login. The login is free, sign up only. You can use your SVC email address and create the sign up for that, and you can start simulating circuit. So only when you draw a circuit, apply the voltage, and if you simulate the conditions, you will get a live picture of what is happening inside my circuit. Okay, so I will show you the live simulation once we study the problems and other biasing circuit.